Okay, so I'm going to be working through the solutions to topic 1, operating with polynomial and radical expressions, skills practice. We're starting with question number 15, which is the square root of 12 divided by 8. Now, when we're working with square roots, it's important to remember our rules, which for square roots containing fractions, we have the square root of a divided by b is equal to the square root of a divided by the square root of b. Now it's important to look at this identity here in both of the directions. So as we look at it from left to right, we can interpret this as that if we have a square root of two things that are being that we're dividing, we can separate them. Now this might have some problem-solving utility, and that it's easier to rationalize or to figure out, to solve and simplify each of these if we treat them on their own. However, sometimes if we're dividing two separate square roots, maybe 4 divided by 8, right? They're both even numbers, and we could reduce that down to 2 divided by 4, which is also equal to 1 divided by 2. Now, so just keep that in mind as we look to these problems. So if we consider the square root of 12 divided by 8, first thing we want to do is try to simplify the fraction on the inside. And I notice that both of these are even numbers. So you can look for the greatest common factor, like both of these numbers are divisible by 4. However, if you just notice that they're even, you want to just continue dividing by 2. That's also an appropriate approach. It'll just take a little bit longer. So both of these are divisible by 4. So if I divide both of them by 4, we can rewrite this expression as 3 divided by 2. Now, we aren't able to remove anything here because there is no square root of 3 or square root of 2 that is rational. So we can just go ahead and either draw a box around it, so we are complete. There is another step where we rationalize the denominator, but we're going to cover that at a later time. So let's go on to problem number 16, where we have the square root of 40 divided by 5. So the first thing we want to look for is, can we simplify the fraction that's within the square root? And we can. 40 is divisible by 5, which gives us 8. So we can immediately simplify this into the square root of 8. Now, as we've worked through in class, if we have square roots that are not perfect squares, the way that we simplify them is we start by looking at all of the factors, and we can break it down to a factor tree. So we can break 8 up into 2 times 4, and 4 can be broken down into 2 times 2. We put an underline under each of the numbers at the bottom of the tree. And then we're looking for pairs here, because 2 times 2, that's 2 squared. So we're able to remove that from the radical. And then everything that's left over, we put right back inside the radical. So that 2 is going to go over here. So first we take the square root of 40 divided by 5. We simplify the fraction to be 8. And then we look at the factors of 8, and we notice that there is a square. There's 2 squared within those factors. So we're able to remove that from the radical, because the square root of 2 squared is 2. And what's left over is just this 2. We can't do anything to it, so it remains within the radical. We put a box around our answer. We can go to the next problem. So go over here and start number 17. So 17, we have some larger numbers here. We have the square root of 75 divided by 9. Now this is where the top identity going to the right is useful. Some people here may notice that 9 is a perfect square. So the first step that I would take in solving this problem is I would use this identity to split them up. So I can rewrite this expression as the square root of 75 divided by the square root of 9. And because this 9 is a perfect square, it's just 3 squared, we can immediately rewrite this again as this is the square root of 75 divided by 3. And this again is because the square root of 9 is equal to the square root of 3 squared, and remember that the square root is the opposite operation of squares, so those cancel each other out, and we're left with just 3. So we still have the square root of 75 to deal with. So what we need to do is the same thing we did in problem number 16. So we take that number and we look at all of the factors. Now I always say in class that I'm used to thinking about quarters in my day-to-day life handling change. So 75 I'm going to break up into 25 times 3. And 25 is a perfect square. It is 5 times 5. So we get a pair of 5s that we're able to remove from the radical. And then we still have this 3 left over. So we rewrite the radical, and that 3 just remains. And this is all divided by 3. Still writing that from the previous step. And there's nothing more that we can do here. So we put a box around it. That's our answer. Okay. On to the next one. Number 18. We have the square root of 90 divided by 8. So, first I'm going to look at these, and I don't see a perfect square. So we can't use the identity where we break it up to make our lives a little bit easier. But I do see that both of these are even numbers. So I'm going to first start by dividing them both by 2. Half of 90 is 45. And that's not a perfect square. And as you notice, I'm always looking and checking for perfect squares because it's the quickest way to just make things easier. When I divided 90 by 2, but now we're going to divide 8 by 2 and we get 4. Look at that. We have a perfect square right here. So now I am going to use the identity that I used in the previous question, which is I'm going to split this up into the square root of 45 divided by the square root of 4. Now 4 is equal to 2 times 2, which is equal to 2 squared. So the square root of 2 squared, those operations cancel each other, and we're just left with a 2. So we can rewrite this again as the square root of 45 divided by 2. Now, again, we have to handle this 45. So I'll write the 45 over here. We're going to break it down. Now this is, anything that ends in a 5 is divisible by 5. A quick way that I think about this is 45 is just 1 5 less than 50, and there's 10 5s in 50, so that means there's 9 5s in 45, and 9, that's a perfect square. That's our 3 times 3. Okay, so we can remove the 3, and then we rewrite our radical, and whatever's left over, this 5 right here, is going to go inside the radical, and don't forget to bring the 2 over. We put a box because there's nothing else that we can do to simplify this. Okay, number 19. We have the square root of 80 divided by 4. So both of these are even numbers. 8 and 4 go actually directly into each other. We can divide them both by 4, and then we don't even have to deal with a fraction here. So that's what we're going to do. So 80 divided by 2 is 40, and then we divide it by 2 again, and we get 20. So we have the square root of 20. Now, 20 is not a perfect square, so as we have done in all of the previous steps, we got to make a factor tree. So draw 20, and we split it up. 10 times 2. 10 we can break up into 5 times 2. Put an underline under all of our factors at the end of the tree. And we can notice that we have a pair of 2's right here. So that's what we get to remove. And then we write a radical symbol. And we look back and we see, okay, we have the 5 left. So we write that right under the radical. And we are done. 2 times the square root of 5 is the answer. Okay. Number 20. We have the square root of 18 over 30. So, first thing, do we have any perfect squares? No. They are both even numbers. So, and they're actually both divisible by 3. Remember, the quick check for divisible by 3 is that if we take both digits, 1 and 8, and we add them, 1 plus 8, that's 9, we ask ourselves, is 9 divisible by 3? Which it is. So then the whole number 18 is divisible by 3. Same thing with 30, although many of you will see that that's just 3 times 10, but 3 plus 0 is 3, and 3 is divisible by 3, so 30 is divisible by 3. The trick will work for all numbers, not just two digits, but even 3, 4, or as many. Okay, so let's start by dividing by 2. We get 9 over 15, and then we'll divide by 3 from here, which 9 divided by 3 is 3, 15 divided by 3 is 5, and we are done. There is another step for rationalizing the denominator, but again, we're going to cover that at a later time. We've got to put a box around our answer. Here we go. Okay, now I'm going to move on to the next section, which is the addition of these radicals and subtraction. So first I want to introduce the identity that we're going to work with, which is that if we have the square root of a, and we have 3 of them, and we add that to the square root of a, that is equal to 4 square root of a. And this is because this is just a count. I keep repeating this a lot, but we're counting that we have 3 of these square root a things plus 1 of these square root a things, which gives us 4 of these square root a things. Now I say a things because when we're counting things, it doesn't matter what it is that we're counting. You know, it's if we're counting coins, if we're counting dollars, or if we're counting chairs, anything. All we're doing is just adding up the number of them that we have. So for example, if I had 10 times the square root of 5 plus 30 times the square root of 5, this is equal to 40 square root of 5. Because we have 10 of them here, we have 30 of them here. 10 plus 30 is 40. Same thing works with subtraction. Now, the tricky part comes from when the square roots, or the thing that is under the radical, is not the same. And that is how most of these problems are proposed. So what we do is we first simplify the radicals down as much as we can, and then if they are the same, we will add them. So I'm going to start by working number 23 to give an example here, which this is 5 times the square root of 8 plus 10 times the square root of 50. So we have the square root of 8, the square root of 50. These are dissimilar. Therefore, we can't say 5 plus 10. This is 15. So we'll start by trying to break down the square root of 8. Now 8 is not a perfect square, so we have to make a tree. 8, it's an even number, so I'm just going to divide by 2. 2 times 4, and 4 breaks up into 2 times 2. So this allows us to remove a 2. Okay, but wait, hold on. We have this 5 out here. So, what I want to remind everyone is that what we're doing over here is we are just simplifying just this part of it right here. This 5 is multiplying by the square root of 8. So whatever we simplify this to, that 5 is going to multiply by it. So back over here at the factor tree, we have a pair of 2's. So we can remove one of those pair of 2's, and then we write a radical symbol, and we look at what's left. This one, 2, is 2. So we are simplifying the square root of 8 into 2 times the square root of 2. So now we have to take this whole piece and bring it back over to substitute it in place of the square root of 8. And the 5 is going to multiply it. So when we substitute things in for other things, it's a good habit to always put parentheses around them. So that's what I'm going to do here. I'm going to write 5 times 2 times the square root of 2. Now I do want to remind everyone with multiplication rules, the order in multiplication doesn't matter. So we could do 5 times 2 times the square root of 2, or we can do 2 times the square root of 2 times 5. It all means the same thing. So I'm going to leave this as it is right now, but yes, we can do 5 times 2 and it will become 10, but we're going to go over and handle this side over here. I might as well just write it. Okay, so we have 10 times the square root of 50. 50 is still not 2, so we cannot directly add these. So what we do, as we do always, is we're going to take that square root of 50 over here, and we're going to make a factor tree. Okay, so 50, again, quarters the easy way to go. 25 times 2. Okay, there's also a reason why I also like to go with quarters, is because when we throw 25 on here, 25 is a perfect square, so it does make our life easier. So this is 5 times 5, right? We can remove that 5. And when we do, we write that, and then we write a radical symbol. We look back at what's left over, just this 2, we write it on the inside. So this 5 times the square root of 2 is what we are going to substitute in for just the square root of 50. The 10 is still there, and that 10 is still multiplying by this. So what we get is 10 times 5 times the square root of 2. Now, like I said before, we can just multiply these. 10 times 5, we get 50. And then we just have the square root 2. Okay, now we do have the same things, right? So this follows directly like our identity that I said before, where we're just counting. We have 10 square root 2's plus 50 square root 2's gives us 60 square root 2's. And if that doesn't make sense, then I would like to ask you the question, what if you had $10 and then you gained $50 more? You would have $60, right? That's just how we count and we add money. And we're just counting these things called square root 2's. And that might seem kind of abstract, but I promise the more we do it, the more you'll get comfortable with it. And it's just because the square root 2 is, as we have been talking about, is an irrational number. So irrational numbers have a long extended decimal that goes on and on forever. It does not repeat, and there is no pattern. So the square root of 2 is just actually the lazy way to save our time writing, because no one's going to write 1.41421356237 ... Actually, we keep writing on forever and all of time, and then we get to the next part, right? And then we have to write it on the next line. So it really is just a time saver. Oh, I forgot the most important part. So we're going to put a box around our answer over here, so we know that we are done. Okay, let's work through another one of those problems here. We're going on to problem number 24. So I like to advise all of my students that this is the trick of adding these square roots where we're just counting them up is pretty straightforward. So that's why whenever there's questions that are assessing the ability to add them, it's always can you simplify the radicals that are out presented to you and identify when they can match up so that you can combine them and when we can't combine them. So here we have 12 and 20. Neither of these are square roots and they are not the same. So we cannot just go straight forward and add them together. So we'll first take our square root of 12 and we're going to break 12 down into its factors. So that is 6 times 2, which 6 is 3 times 2. So we have this pair of 2's right here that we get to remove, and that 3 that's left over, so we put it right back under the radical. So this is now what we get to substitute back in for this square root of 12. So I write that here, plus, now we have 8 times, okay, we have the square root of 20, that's not a perfect square, we got to break it the factor tree there. We have 2 times 10, and 10 is, make a little divider so we don't get mixed up, 2 times 5. So we have our pair of 2's right here, and we have that 5 left over. So 2 times the square root of 5. Now remember, again, this is one of those where we have that 8. The 8 is multiplying here. And this 2 times the square root of 5, remember, we didn't break down and get this number including the 8, we just did it with just the 20. So this is going to come over here, we're going to substitute that in for the square root of 20. So we have 8 times 2 times the square root of 5. Okay, we're done over here, so on the next line I'm just rewriting this, plus 8 times 2, 16, times the square root of 5. Now, square root of 3, square root of 5, these are not the same, so we cannot add these. We are done. We put a box around our answer, and we can go to the next problem. 25. We have the square root of 44 plus 4 times the square root of 20. Now, everyone, it's a key part of working through a bunch of math problems. If we already solved one of these square roots of 20, don't make yourself do extra work, right? This is the part about seeing patterns too, and using those patterns. If you were to just work through, when we work through a bunch of different problems that include square roots, it's very likely that some of you will start to see the patterns of, oh, this is how they quickly simplify, if there's especially common ones. So we're going to reuse that here. And on this line here, I'm just going to rewrite it as square root of 44 plus 4 times, so we said the square root of 20 turned to 2 times the square root of 5. 2 times the square root of 5. Alright, so that's just going to be 4 times 2, which is going to be 8, but now we still have this 44 to deal with. So let's break down 44 into a factor tree, which is 4 times 11. Anytime you have a 2-digit number that repeats, 11 is a great factor to look for. And 11 is a prime number, so we can't do anything with 11, but 4 we can break up into 2 times 2. So we remove the 2, and we write our square root symbol, put the 11 back into it. So that's going to come back over here. We have 2 times the square root of 11 plus 8 times the square root of 5. And again, 11 does not equal 5. We cannot add these together, so we put a box around our answer, and we can go to the next problem. Alright, I'm going to work a subtraction problem now. So same thing as the previous one, except we just need to be careful about signs and make sure we're doing addition with negative numbers properly. So this first one I'm going to work out is number 29, which is the square root of 72 minus 4 times the square root of 12. Alright, so 72 breaks up into, it is an even number, so I want to divide by 2 first, and we get 36 times 2. Now we break 36 up. It is a perfect square into 6 times 6. We can remove that 6 immediately. And we just have this 2 left over, so we tuck that back under the square root. So I'm going to come back over here, and we can rewrite the square root of 72 as 6 times the square root of 2. We're subtracting here, so we're going to be careful about that at the end. And then we have 4, and now we need to handle the square root of 12. Okay, so 12 breaks up into 6 times 2, and 6 breaks up into 3 times 2. So we have that pair of 2's there. So this becomes 2 times the square root of what's left over, just that 3. And remember, this 6 does not count as something that we are looking for that's left over. It's only the ends of the tree. And it's only the ends of the tree is because we broke this 6 up into the 3 and 2. If we use the 3 and the 2 and include the 6, it's a different number. If we look back at the ends of any of these trees, 6 times 6 is 36, times 2 gives us 72. Over here, 3 times 2 is 6, 6 times 2, that's 12, right? So if we look at all of the ends of the trees combined, those are the total prime factors that create the number that we're breaking down. Okay, so again, we're substituting. So we have that 4. That 4 is multiplying here. So we're going to substitute this back in just for this square root of 12. So this is 4 times 2 times the square root of 3. So we have 6 times the square root of 2 minus 8 times the square root of 3. 2 does not equal 3, so we cannot combine these. So we put a box around our answer. Turns out we didn't have to be too careful about the negative, besides just making sure we wrote it there. Okay. Let's look at problem number 32. This is 7 times the square root of 72 minus 2 times the square root of 2. Now again, if we see this pattern, we just broke down the square root of 72. We have it right here. We've already done the work. Let's use it to our advantage. So I'm going to write that 7. And remember that this square root of this is the square root of 72. Right, so we're going to substitute that in just for the square root of 72. So this will be times 6 times the square root of 2 minus, now 2 is already prime. We can't break this down anymore, so it's just 2 times the square root of 2. Okay. Now, we have 7 times 6. It's going to give us 42 of these square root 2's minus 2 of these square root 2's. So, luckily this number on the left is larger than the one on the right, but we do have 2, and 2 is the same number under the radical, so we can directly subtract, and 42 minus 2 is just 40, and then we have the square root 2. We put a box around our answer. Now, we've covered dividing, adding, and subtracting. All that's left now is multiplication. So the multiplication identity for radicals is the square root of a times the square root of b is equal to the square root of ab. Now again, just like the identity division, or the identity for division, the identity for multiplication is best viewed to the right and to the left. So let's look at that real quick. Going to the right, it means that if we have these two numbers, we can just combine them. Having multiple radical symbols can make an expression or a equation look very messy. and a lot of what we work on in math is just trying to communicate numerical information, and clarity in communication is important. So sometimes combining these can simplify, what it is that we're showing. So we don't have all of these crazy symbols. Sometimes that can allow us to rationalize and take care of the square root and make it simpler. So we can use that to our advantage. Just to remember, we can combine them together. And it's also, the reverse I think is even more valuable, is where we can separate them into two separate square roots. So let's look at a couple of these. So I'm now working from problem set number 4, which is operating with algebraic radical expressions. But actually no, I'm going to do a one problem here first, just to show how this works. If I have the square root of 2 times the square root of, let's see, 45, we can just directly combine these into the square root of 2 times 45, which is equal to the square root of 90. Okay, now with some variables involved too, if I have the square root of 2xy times the square root of 3xy, what we get is, combining them, we just multiply directly. We multiply the constants first, and then we multiply the variables. So 2 times 3, we get 6. X times x is just x squared, and y times y is y squared. Now, this is where breaking them apart can be used to our advantage, because I think it really illustrates what we're doing here is that if I break this into the square root of 6 times the square root of x squared times the square root of y squared. Now, I hope everyone is seeing that this and this, the square root of x squared, right, the square root is the reverse operation of squaring. So they cancel each other out. Just like if I had to take 4 and I multiplied it by 2, we get 8. But then I divide by 2, we're right back to 4. So both of these cancel out, and we're just left with x and y. Now the square root of 6, just like we've worked on all the other problems, we have to break down into a factor tree, which 6 breaks into 2 times 3, but we don't have a pair. So there's nothing we can do. It's in its simplest form. So it just stays the square root of 6. So altogether here, we get, and we like to put, just as in the other problems where we had like 2 times the square root of 2, we're going to put this x and the y just on the front of the square root, and that's just because of a convention. We just do that to normalize the way that we write things. So xy times the square root of 6. Okay, so now I'm going to go through and I want to work on problem set number 4. We're going to look at number 1. Actually, that one's kind of worked out there, so I'm going to leave that one a little bit of an exercise with some scaffolding to guide you through it. We're going to look at number 2, which is the square root of 120 r to the 5th power times the square root of 80 r to the 4th power. Okay. Couple approaches, but there's a lot of simplifying in these, so let's get to work. 120 and 80, we need to break those down. Just like before, because we have two things that are multiplied together, 120 times r to the 5th power, we can separate them and treat them individually. I'm not recommending all of the time to write out every single line, break this into the square root of 120 times the square root of r to the 5th power times the square root of 80 times the square root of r to the 4th power. This might make it easier for you, and if this does, absolutely do it. Sometimes when I'm working through things, I just got to, go through, break it all down because I have to prove it to myself. If that's what you got to do. I support that. But also, if you want to save time and not write as much, I also respect that too. So what I mean by that is that we can just treat these separately and individually within this big square root. And remove things without worrying about the other thing. So I'll show you what I mean by that. So come over here, I'm going to write 120 and we're going to break it down to its factors. I tell everyone if we see the 0, let's use 10, and then 10 times 12. So 10 is going to break up into 5 times 2. 12 we can break up into 2 times 6, which is going to break up into 2 times 3. So we have a pair of 2's here, and that's it. No other pairs. Okay, then we have 80, which we can break up into 2 times 40, and 40 can be broken up into 20 times 2, and 20, I'm going to put an underline around those 2's. It's getting a little messy here, and I don't want to forget about them. The 20 there is going to be break up into 2 times 10, and the 10 is going to break up into 2 times 5. Okay, so we have one pair of 2's right here. We have another pair of 2's right here, and that's it. So we can remove 2 2's, and then what's left over here? Just a 5. So 80 is going to simplify into 4 times the square root of 5. Over here, we're able to remove our 2, and then we have the square root of 5 times 2 is 10. 10 times 3 is 30. Okay. So remember, these are just the numbers that we solved. So we can go through and substitute them in over here, which will have 2 times the square root of 30 times the square root of r to the 5 times 4 times the square root of 5 times the square root of r to the 4th. Okay, now we have all of these r's. So we have 5 r's and we have 4 r's. We can combine them together because the identity says that if 2 radicals are multiplied together, we can combine them. So that just means we have 5 plus 4, we have 9 r's. Okay, so I normally have a little bit of a quicker way of doing this, but I like to write it out to illustrate. So it's 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we're just going to circle pairs. So we have 1, 2, 3, 4, and then there's going to be 1 left over. So the way that I really think about this, though, is that I look at it and we have 9. So I think about what's the next lowest even number. So if we subtract 1 from 9, we get 8. And 8 is divisible by 2, an even number is. So when we divide 8 by 2, that gives us 4 pairs. And remember, for each pair within a radical, we can remove a single one of them. So we have these 4 pairs, and then there's 1 left over, right? That's what we're seeing right here. So, and remember, this is all 9 of them, so we're working with both of these. I'm going to rewrite here 2 times the square root of 30 times 4 times the square root of 5 times, we removed 4 r's, so that's r to the 4th power, times the square root of r. Okay. So we can clean this up a little bit now by combining all of the things on the outside of the radicals and all of the things on the inside of the radicals. So 2 times 4, we get 8, times r to the 4th power. And then we have the square root, 30 times 5. Well, 3 times 5 is 15, and then we just add that 0, we get 150. And then we have r. Now 150, we do need to check to see if we can simplify. So 150 is 15 times 10, which is 3 times 5. 10 breaks into 2 times 5. We do have a pair of 5s. Okay, so we can now remove a 5. So we get 8 times 5 times r to the 4th power times the square root of what's left over? We have that 2 and we have that 3. So 2 times 3 is 6. 8 times 5 here, we get 40. Oh, don't forget the r over here. I almost did. And then we have r to the 4th power times the square root of 6r. And we draw a box around it. Now, I know that and can respect that this is a lot of work. There are going to be steps in here that you will learn to skip and jump through and jump past. But at the beginning, it is helpful to write out all of these steps, and I urge you to think about what it is that we're doing. A lot of this stuff comes down to critical thinking. That means that we're trying to make connections and identify relationships and patterns. So the fact that we see things happen multiple times across different problems, if your mind is picking up on any of those, continue to think about them, as they're very important, and it will lead to more problem-solving avenues as you continue to work through math.